Let's talk about Kullback-Leibler divergence. Now say you have a random variable x, which is sampled from some distribution p of x. So let's say p of x looks like this. So this is the probability. This is, say, the probability of finding x to be between, say, a and b. Now let's say that we have the value of x and we want to transmit it to a receiver using binary digits or bits. And the question is, how many bits do we need to transmit the value of x to your receiver? And this assumes perfect communication. The minimum number of bits required to transmit the value of x is given by the entropy of x, which is equal to the negative integral of p of x log base 2 p of x. And we're using base 2 because we're dealing with binary digits. Now suppose that you have a second distribution, q of x, which approximates your p of x. q of x approximates your p of x. Now let's say that despite x being picked from p of x, we want to use some coding scheme using q of x to transmit our data to the receiver. In other words, x comes from p of x, but we want to use q of x to come up with a coding scheme to transmit to our receiver. Now the question is, how many bits do we need to transmit that information to our receiver? So let's call that h of x using q, and that becomes equal to the negative p of x, which is the actual probability of picking x from the true distribution p of x, log to q of x dx. Here we're using q of x because we want to calculate the number of bits needed to transmit x using q of x as our approximate distribution. Again, the first value calculates the number of bits needed using the actual distribution p of x as your basis, and then the second one calculates the number of bits needed using an approximate distribution, which is q of x. Let's change the first variable to be h sub p of x. Now, Kullback-Leibler divergence asks, how many additional bits do we need to transmit the value of x using q of x, which is our approximate of p of x? Next, what we need to do is subtract hq of x minus hp of x. And this is the additional bits needed to transmit the value of x. And this is your Kullback-Leibler divergence, where your x is sampled from p, but you're using q to transmit the information about your x. Let's plug in the values of the integrals. So this becomes negative integral of p of x log q of x dx minus negative integral of p of x log p of x dx. Now this becomes negative integral p of x log q of x dx minus the integral of p of x log p of x dx. And then we can combine the integrals to be equal to negative integral of p of x log q of x minus p of x log p of x dx. We can combine the logarithms to be negative integral of p of x times log q of x minus log p of x dx. And using rules of logarithms, we can simplify this further to be p of x times log q of x over p of x dx. And this is the final form of your KL divergence when you're trying to transmit the information of x that's drawn from p given an approximate distribution q. Now it follows that the only way the KL divergence will be equal to 0 is if p of x is equal to q of x. KL divergence is not symmetric in the sense that the KL of p q is not equal to KL of q